sometimes you may want to know what grade is, but they're not next to each other. Good call. That's a good call. Are you going to the restroom? All right. So let's start today. Couple of things. You got a bit of a reprieve. I didn't put out the assignment on Sunday night itself. I thought that might be cruel or usual. But there will be a new assignment developed for tonight. This will be homework 3. It will cover some elements of greedy. It will also probably cover some stuff from here now, so that you don't have to start working forms right now. You can start working on the greedy part, and then as we go through with this, we'll see more stuff close. Okay, so we've seen 3 sort of main paradigms for designing algorithms so far, right? So we've seen divide and conquer, right? So which is basically recursion, right? With induction for correctness and recurrence relations for time, right? Then we saw dynamic programming, which is a kind of smart recursion. Right? With the caveat that you have to design recursively but implement bottom-up, which means your correctness proofs still work the same way. Because generally speaking, correctness proofs can often be orthogonal from the runtime issues. So the recursion itself is enough. But then to analyze the runtime, you do the unrolling, and then it often ends up being a much more simple analysis of the runtime, right? So you still use induction for correctness, but you use sort of a direct analysis for runtime. And it's often a lot easier. Right? The hard part of the dynamic programming is making sure you've is getting the optimal substructure recursion going so that you can show that that's going to be correct, and then unravel. So this is all the surface here. Then we talk about greedy algorithms, right? Where the proof of correctness works very differently. So the proof is by comparison to optimal, and it's not as structured as we've seen for other problems. Right? You have to reason very carefully in each case what it's going to look like, and it's much less cookie cutter. You really have to look at the problem carefully and reason. There's some basic guidelines, right? So think of an optimal solution, think of the first point where it disagrees with agree, see if you can change. There's a basic framework, but it's not that clean a framework as we've seen so far. And again, we've never really talked too much about running time, but with greedy algorithms, often a running time issue with, you just have to look at the code and what it's doing, see how long it takes to make that greedy step, and then make sure that it can converge, right? So basically, the running time analysis usually consists of how long it takes per step, and then how many steps, right? And in some cases, it's very easy. If it's a discrete problem, usually this is not a problem. You can analyze it. But if you're doing something like local search, right, which we've seen as sort of a, you can think of it as a variation on greedy methods, right? You almost never have anything here. You almost are never going to get a correctness result here. And again, but then these become big issues. How much time does it take per step, and how many steps you can do, right? And so that's the landscape of tools that we've seen so far for designing algorithms. When I compare that for greedy and local search. And in some sense, they're mostly orthogonal from each other. I mean, they're related but different. Sometimes for some problems you need one of these, you can't use the others. Especially with things like dynamic programming, often that's the only way you can solve the problem optimally. You can't do something else. So what we're going to look at today is both a problem and a method for solving problems. So it's a weird thing where all of these techniques are just techniques, right? It's a strategy for solving a problem. The thing we're going to discuss next is both a problem itself, but in the process of solving the problem, it reveals some more general ways of thinking about how to solve problems, right? And this would connect up to much larger frameworks for thinking about problem solution involving things like linear programming. Right? So you can think of flows as a kind of a gateway drug into linear programming, which itself is a gateway drug into non-convex programming, which itself is a gateway drug into non-linear, so non-convex programming, at which point you just go mad. So we're not going to go mad this class, but we will try to get part of the way there. It's good. It's fun to be mad. So flows and cuts, and that's the topic of the discussion today. So that's what we're talking about. Okay. And so, like I said, it's both a problem and a problem solution technique. So let me define the problem first. And so let's just talk about cuts, because they're the most natural question to talk about, now than related to physics of flows. So the object of study here is going to be a graph. Okay, so let's just draw a graph. So we have some kind of graph. I'll just draw a graph here. Okay. And just so we can talk about it. So the first thing I want to define is a cut in a graph. Okay, so what is a cut? A cut is a subset of edges that, when removed, disconnects the graph. That's all. So for example, I could take all the edges adjacent to the vertex A. Right? So edge AH and AB. If I remove those two, A would be disconnected from the graph. That is a cut. I could take all the edges adjacent to G. So GH, GD, and GF. I could remove all these edges, and G would be disconnected from the graph. But I don't have to do that. I could, for example, take edge, let's see, CD, IF, and HG. So this is an example of cut. And I'm going to show you by just drawing a line through all the things that I actually end up cutting. So if I cut these three edges, as you can see, I've cut all connections from the left to the right. That is also a cut. because it disconnects the graph. So it's a very simple idea. It's a subset of edges that, when removed, disconnects the graph. Okay. And one interesting variant of this question, which will come up a lot more in what we want to study, is something called ST cut. An ST cut is again a subset of edges that, when removed, disconnects S and T. So not everything, but S and T specifically. So for example, if I looked at those three edges that I decided to cut with that red line, would that be an AC cut? No, because it has disconnected the graph, but A and C are still together. What it would be, though, is an AE cut, because it now separates A and E. It could also be a BG cut, or an HF cut, or an HD cut. It could be all of these things. So an ST cut says, look, I want you to focus on two specific vertices and delete edges to disconnect these two. Put them in separate components. A general cut is just disconnect something. Okay, so this is a special, more constrained version of that. Okay. So whenever you say, so one motivation for studying cuts is as a dividing function strategy. So this comes up a lot, for example, in sort of mapping computations on multiple nodes in a hardware system. So you can think of the nodes of this graph as, say, processing units. You can think of the edges either as physical wires or some kind of communication channel between processing units. And you might want to ask yourself, can I delete as few communication channels as possible to separate out communication channels? And one reason you might want to do that is not because you're actually going to delete those communication channels, because you're saying that for the most part, these units can run separately from each other, and they only occasionally have to talk to each other. And if any of you work in parallel processing, you will know that one of the holy grails is to make sure you can parallelize as much of your work as possible. Right? The more you can parallelize, the faster your process will run. But to parallelize, you will just need to say, okay, you can do your thing separately, you can do your thing separately, and you can run them all in parallel. If they have to talk to each other, that creates sequentiality, right? Okay, I gotta wait for you to tell me something. Okay, now I have to tell you something back, and that slows things down. It makes it sequential. The more parallel you can make things, the better. To make things parallel, you have to make sure that you don't need communication between things. And the next best thing is to say you have very little communication. So here the idea is that you want to disconnect your graph, disconnecting as few of these things as possible. So you want to find like so your picture in your head might be something like, I have one piece of my graph here, and I have one piece of my graph here, and there's one point here where as long as I can do most of my work here, I can do most of my work here in parallel, and every now and then I have to communicate across. Okay. All right. Such a question. So the question of saying, I call it the problem of the min cut. Okay, is find a cut, which we've already defined, of minimum size. And of course, a cut is a subset of edges. So when I say minimum size, I want to remove as few edges as possible and still disconnect the graph. Now, I try to motivate this by talking about parallelizing computations on a certain architecture. You can think of this from a different point of view as well. You can think of this as a vulnerability analysis, right? Suppose you have a communications network, and outside entities are trying to attack your communications network. What is the minimum number of edges they need to sabotage to disconnect your network? So, as usual with algorithms, you keep coming back to military terminology, but one connection here is that you have, again, let's say your army has got some communications methods. They have different channels of communication. They may have actual line of sight communication. They may have people relaying messages. They may have radios. And if you want to sort of disrupt an army's progress, one thing you want to do is disconnect communication. And so then you say, okay, what is the easiest way to disconnect communication? From an attacker's point of view, you want to do it efficiently. From a defender's point of view, you want to say, look, I don't want my system to be vulnerable. If there's a single point of failure in my system, that could cause the entire system to go down. Right? So just from a point of view of designing a reliable and robust system, you want to have many points of failure. You don't want a network that looks like this. If you've done a network where there's one edge that fails, if those two endpoints fail, you're in big trouble. You want to have multiple redundancies. So again, the min-cut comes up. It's a way of doing a diagnostic on your system to see how vulnerable it is to attack. And in fact, historically speaking, the discussion around cuts and flows goes back to the early stages of thinking about the U.S. highway system. And Eisenhower sort of was thinking about the Cold War and Soviet attacks in the U.S. and how it would disrupt communication. One of the motivations for building the national highway system was to provide multiple points of contact, so that there was no easy way to disconnect the ability to transport material across the country. So there was a motivation. So the study of flows and cuts comes way back from there. Okay. So one classic question you can then ask is, how do you find, given a graph, find this minimal cut? And we'll talk about it in a bit, how to do that. But that's one of the questions you might ask. A question that is sort of, so there's a meta theorem in sort of unstated meta theorem in algorithms. Right? There's some quantity. You can either minimize it or maximize it. Usually one of these things is easy and one of these things is hard. Depends on the problem. But generally speaking, minimizing can often be easy, maximizing can be hard. So for example, you've heard of shortest path problem. So if you find the shortest path between 2 points, you can solve it. Find the longest path is very hard. That's an intractable problem. Min-cut, we will tell you how to solve it. It's not trivial, but you can solve it efficiently. The corresponding problem, when I flip this around, so now you want to find it's a little harder to give you a sort of a practical motivation. It has a very nice theoretical structure to it that shows up in other problems. But I'm not going to give you a practical. There's a good practical reason to study this. But it's a very interesting problem. It's also very common. It's actually impractical. But it also comes out of the context of class. And there are other variations of this question you can ask. So that something you can report on in my flow. And I want to emphasize one thing about this, that this is a purely structural question. If I give you a graph, right? This is a question you can ask with a graph. What's the size of the min-cut? What's the size of the maximum? You don't need to know anything else. It's just a basic property of it. Okay. All right. Yes.
So when we say, I guess, how do you define? I was expecting someone to follow find a cut of minimum size, because what is the end goal of the min cut? It's just to disconnect as many nodes, like to evenly split the graph.
Okay, good. One variation, another variation, which is called graph bisection, is to say find a cut at minimum size, and this is the parallel processing sort of more motivation comes from there. Well, it's not going to be a minimum size, of small size that splits graph into equal, and again I'm going to put quotation marks here, but this sometimes it doesn't have to be exactly equal. And you should hopefully see why this would be a good thing if you remember how divide and conquer works. Divide and conquer says I want to split things up so they're roughly balanced, right? So that's something you want. And you want this to be a small size because hopefully your merge process is going to be simple. Right? If I can remove one edge and divide it into 2 parts of equal size. So there's a very nice, for example, property of trees. In a tree, there always is one edge that is guaranteed to divide the tree into a part, let's say it's a binary tree, so into a part of size roughly 2/3 and a part of size roughly 1/3. So each part is at least 1/3 in size. So this is not balanced, it's not half and half. I can't always guarantee that. But I can always guarantee at least 1/3, 2/3. And if we remember divide and conquer, that's not a bad thing. If you have constant fraction on each side, you can still get sort of good behavior. But it's not obvious facts. It's worth thinking about. Why is it that I can always do this in a tree? How would I go about doing this? But you can't do this. In a general graph, it's much harder. This is a hard problem. If you want to find a cut that's of small size, but also balances things into roughly equal parts, this is actually an intractable problem. Unlike min cut, it's like going just find a cut of small size. Okay. But that goes to your question, I think, right? So this is the kind of thing you might look at. Right? So as you can see, there are many questions that sort of boil down to finding a cut which has a certain property to it. Right? Either the cut is small, or the cut is big, or the cut balances things here.
Is this kind of subset of finding bridges and articulation points in the graph, or?
What's a bridge?
A bridge is edge which, when taken out, also disconnects the graph, right?
Good. Suppose a graph has a bridge. What is the size of its min cut?
1.
Suppose a graph doesn't have a bridge.
So like it would be greater than 1.
So they're related.
Okay.
Yeah. So suppose a graph is articulation point. What's the size of its min cut?
So articulation point is if you take the node out, it disconnects the graph.
So what's the size of its min cut?
1.
Really?
Number of edges connected. Yeah.
That you create.
Could be whatever.
Yeah.
So it's not clear.
Okay.
So they're related. They're not exactly the same. Yeah, and a min cut is always a set of edges, not a set of vertices. If you want to delete vertices and all the attendant edges, that's a different problem. So for example, speaking of bisection, here's another fun fact. I was talking about trees, right? Take any planar graph, right? There is always a way to remove a small-ish set of edges to divide the planar graph into two roughly equal parts, where small-ish is square root of n. And n is the number of vertices. You don't need to know the number of edges because the planar graph has to have a linear number of edges, because like that's exactly at most 3 minus 6 edges. So for trees, one edge suffices to get a balanced subset. In a planar graph, you need something like square root of n, but you can always do it square root of n. And if you're wondering why square root of n, let me give you a non-proof. A non-proof is, think of a grid. If you think of a grid and there are n vertices in the grid, that means each side must be something like square root of n. Right? So square root of n times square root of n, that's a grid, that's a planar graph. And if I just take off one row or one column, one row or one column, that will disconnect the graph. And that means square root of n. So this is not, of course, not a proof or anything, but it's a kind of intuition as to why you might need square root of n. The fact that you only need square root of n is very, very deep. It's called the graph separator theorem. There are many, many different proofs of it. Some of them are purely geometric proofs. There's a sort of underlying geometry of planar graphs that allow you to prove this, which I won't get into here. But so there are a lot of nice things you can say once you start talking about cuts in graphs, and so there's lots of fun topics. But we won't go into all of that right now. We just want to focus on the basic problem of an arbitrary graph finding it. It turns out that if you want to reason about, well, at least deterministically, if you want to reason about cuts in the graph, it helps to reason about a related concept at the same time. And that concept is very different. It feels very different. It's not, doesn't appear to be a static property of a graph. And yet, it's very closely related to cuts. And that's the other word I can play, flows. And as we go on in the course, we'll talk about something called duality. That there are notions that somehow, if you look through a mirror, you get one versus the other. But they're sort of inextricably linked in a way that you really can't separate one. So flows and cuts are like this. They like this duality that lives together. You can't really look at one without looking at the other. Okay. So let's talk about flows. So again, we'll go back to our graph. So let me just get our graph again.
When you say duality, does it mean like that all the cut problems can be converted into row ones and vice versa?
Okay. So let's look at our graph again, and now we'll start adding some information to the graph. And what we're going to add is we're going to think of this graph not as a graph, but as a bunch of pipes. Okay. All the edges are pipes. All the nodes are places where water flows through. And because they're pipes, they have amount of water they can carry. Some pipes are big, some pipes are small, some pipes are frozen, and others burst, if you would call them all. And so we'll write down a number associated with every edge, telling me how many units of water to involve. Okay, so I'm going to write down a bunch of numbers here. So let's say I know this is 10, 5, 6. Just write down a bunch. Okay. So these are called capacitors. I am also going to do another thing to this graph, which I didn't have before. So I'm going to add all kinds of interesting things to this graph that I didn't really think I was going to add. I'm going to put the directionality on it. Okay. So those directions. And finally, I'm going to add two things. I'm going to add a source and a sink. So a source, since I talked about pipes and water, think of the source as a place where the water comes from. It's a source, it's a fountain, it's an underground river, whatever. So you can think of an infinite supply of water coming in. The sink is where the water goes out. Maybe this is a reservoir, not a reservoir, this is like a place that goes into people's houses. So again, since I can drain out the drains, it's an infinite sort of sink for water. So there's water coming in at A, there's water coming out at E. And of course, to get from A to E, it has to flow through all these pipes in the right direction. Okay. And again, because these pipes have capacity, only so much water can go through the pipe. Right? I can send 15 units of water through out of A, 10 and 5. But once it gets somewhere, they'll get stuck if we don't have enough way to pull other water out. Right? I can't just put as much water as I want. In other words, pipes can only carry so much water, and a vertex that's getting water in and water out has to balance it. There's no leakages. You're not allowed to have things leak. So I can't lose water, and I can't produce water from nowhere. I can't be getting in 5 units of water from behind me and then sending out. No water manufacturing or loss of time. So these are what are called conservation constraints. So let me just write them down since I just said them. So water comes from source, water goes to sink at all other vertices. Water coming in is equal to okay. And then there's also capacity constraint. An edge carries water up to its okay. So far I've just given you a specification and a bunch of constraints. I have not yet told you what to do with all this. Well, what I want you to do with all this is maximize flow out of the source. Okay, so let me just move this back down so you can see. So again, we're given a graph now with these directions, with capacities, with the source and the sink. We have rules about the flow of water that reflect the fact that water cannot be produced or destroyed except at the source and the sink, which is why you have a separate rule for them. And the goal is to see how much water you can push through the system. So again, if you apply my meta theorem to this, suppose you want to minimize the flow of the source. Is this easy to solve? Just don't do anything. Answer 0. That's easy. It's the max flow, it's a little bit harder. Right? How to maximize the flow. And again, as a motivational point, think of why this might be interesting. Suppose you're a traffic engineer and you're designing a new sort of set of highways, you're trying to modify lanes on the highway, trying to design where flow is going to go. What you want to know is, okay, how much flow is there in the system? How much traffic can I push out through this network of highways at rush hour at 5 p.m. on a Friday? Right? And you use calculations of this nature to say, okay, this is the amount of flow I expect to push out. This highway has 3 lanes, this one has 5 lanes, that's capacity. There are junction points where cars come in, cars go in, and hopefully there are no accidents. So whatever is going in comes out, right? And new cars are being produced at the same time. So, and you want to make sure you get good throughput. And so this problem of maximizing flow and source is a network design problem sometimes. Or it's a way of saying, given a network, what is the amount of flow it can carry? Okay. Does this question make sense? So this is a very dynamic problem, right? Saying, okay, I want to push this stuff out, I want to do it with it. But I mentioned these two problems together for a reason. There's a connection. And maybe you can think about what that connection is. What could possibly be related? What could the possible connection be between cuts and flows? Based on your understanding of what these things are. Just intuitively.
Can you remove some edges without affecting the flow?
Can I remove some edges without affecting the flow? It's possible, right? For a given graph, I say, okay, I have some algorithm that maximizes the flow. It says I can flow X, 10 units of flow to the source. Now I remove an edge. It might be I still can do it. Maybe. It's entirely possible, right? There may be some irrelevant edges that don't really make a difference. Right, I see where you're going. Anyway, so yes, what could be a potential connection? What I wanted here was actually, I don't want rigorous reading. I want some kind of sense of way. That's where all these things start. That intuition. Yeah.
If it becomes disconnected, there is no way that water can go from this part to this part.
Very good. First observation. If the graph were disconnected, then there's no way for any flow to go from one part to the other. The flow would be 0. So there's some connection there between disconnecting the graph and the flow. Good. So let's try to build an observation. Yeah.
Maybe bottlenecks, because the
Same one.
What's that?
Check here.
Since you're minimizing the cut, you're minimizing the flow between the two, I guess, pathways. So you're identifying where, I guess, the smallest flow can travel.
Right. So there's some notion of a choke point, right?
Yeah.
That if you're worried about where the flow is going to go, there's some kind of choke point, like somebody on the highway and they closed off all but one lane. It doesn't matter what else you have traffic coming in. We all know that eventually that choke point is going to decide what can go through. Even if you have 5 lanes, 10 lanes of traffic coming in, that could make things worse, right? You have all this traffic lanes, so they stop right there. So there are choke points in the network that could prevent the flow from increasing. But some of these choke points also would imply that it's easy to disconnect. Because if you had lots of ways to flow, that means they're not good ways to disconnect. You need to do a lot of work to disconnect. Okay, that's good. That's good. We're getting closer. Can we sort of come in for the kill now? Sort of, put all the ideas together.
Would the edges on the min cut identify the maximum flow? Be the total constraint for the maximum flow.
So now we have a more specific claim that somehow if we looked at the edges in the min cut and looked at how much they could carry, that should constrain how much flow we can push through. So let me write this down. Somehow the claim is that the max flow is less than equal to the capacity of edges in the main cut. Is that what you're saying? Yes. Let me make another observation which is related to this. Let me claim that I can actually remove this word. You still believe it? I remove the word min. That the max flow is less than equal to the capacity of the edges of any cut. That seems plausible. I'm not asking for proofs right now. I'm just trying to build some intuition. But that seems kind of, I don't know about that. I mean, what do I think about this is that this is the smallest cut. If the flow is less than this, it has to be less than any cut that's bigger than this. Right? Well, in which case, what is stopping me from doing this? Any flow has to be less than the capacity of any cut. So if you think of all the flows, so I like to think of this, when I think of duality, right, I like to think about this in a picture. So the way I think about it is, I have all these flows down here. Like all the flows. And then there's the one that's like striving to get to the top, which is the max flow here. And I think of I have all the cuts. And because I have this, I can think of all the cuts down here. And then there's the lowest cut right there. And this is kind of what we're saying. That the best flow is not as good as the worst cut. The max flow is less than equal to the min cut. Of course, the question is, well, you know, will these two like blobs ever meet at a point? Is it in fact the case that they touch, that the max flow is min cut? In fact, this is what turns out to be the case. So if you drew this picture, again, this is what really the picture looks like. This, of course, requires a proof. This is what the picture is. That the max flow is has the same value as the capacity of edges in the main cut. The capacity of edges in the main cut gives you a flow. Now we kind of intuitively seem like this is reasonable. This should not feel reasonable to you at all. I mean, in other words, there's no good reason why this should be the case, because this is something stronger. Not only is it saying that, look, there's a constraint that you can't push that much flow if there's no edges to push it through, which is the reasonable part, but you can in fact match it all the time. And you think, well, you know, maybe there are more edges, but I can't quite get my flow because of some other bottleneck. It doesn't seem obvious at all, right? And what we'll do is we'll actually argue that this is in fact the case. And what this does is basically it says two things. So we looked at greedy algorithms in particular and tried to prove optimality. Prove that something is optimal. We're trying to reason what optimal does, it's really hard. What I'm saying here is that in fact, the way to show that this is optimal is to produce something there that's optimal, and vice versa. This is where this duality comes in. These are both two different optimizations. But to prove one side optimal, max flow, you can actually reason about the other side, which is the min cut. And to prove the min cut, you can prove max flow. So it's a way of giving you a proof of correctness, essentially. That in other words, if I want to show that I've pushed as much flow as I can, I need to be able to show that there is a cut of that size now in the graph. Right? So the cut says I can't push any more flow. So this is a max flow. I couldn't have come up with a better cut because I would have violated the fact that I had this flow. So the fact that I can show that there's a flow that equals the value of a cut also proves to me that they're both optimal, because this picture doesn't go any further down, they only touch. We've already argued that every flow should be less than every cut. So if I can find two that are equal, they must both be optimal. So this is a very different way of proving optimality. Like I said, this is a special example of a more general idea of what is called linear programming duality. That to prove something optimal, you write down this other auxiliary function, which is also an optimization. But to show that one side is optimal, you need to show that something happens on the other side. And the two of them together is what gives you the proof of optimality. Okay? So this is not going to look like the kinds of optimal proofs we had. Any questions so far? Before we start trying to think about this more.
So, like you said that minimum cut is depends on the number of edges, right? So, like if there is a graph where there are two minimum cuts of size 2, we would need to consider the one with less capacity for this relation to hold the maximum flow.
Correct.
Yeah.
I would look at the capacity of those edges. So in other words, in my min-cut problem, I could generalize it by saying every edge has a capacity, and the definition of the min-cut is a set of sum of capacities, is a minimum edge, is the sum of the capacities of the edge set that disconnects the graph, and I want a minimum such sort. Yes.
Does the direction of the edges matter? Because if
For flows it does.
Yes.
For the cuts it doesn't. You'll see why. That's the thing, right? We're relating something that seems very dynamic, and you're pushing flow through edges, you're doing something, to something that is structural in the graph itself. And again, intuitively it makes sense. Okay, there's some basic bottlenecks I can't get around, no matter how hard I try. Right? So it's a structural property. I think to me, what's more surprising is that they're actually equal. It's not hard to come up with structural barriers that prevent you from optimizing something. It's a bit more unusual when they actually do give you the answer itself, the fact they're equal. So in fact, in duality, this is what is called sort of weak duality. Right? This generally is easier to show, that one side is less than equal to the other. The fact they're equal is much harder. So for example, this works for linear programming, but it doesn't work for integer programming. It doesn't work for other kinds of non-convex programming. Okay. All right. So what we're going to do now is actually think about how to reason about this, because that's going to essentially, that is going to give us an algorithm for computing mass flow and also for computing. Right. So I'm going to think of the flow side of this for now, just because it's more convenient, and I'm going to start reasoning, try to construct an algorithm for mass flow. And what I should say is that I should mention here now is that in order to reason about flows, we need to represent our flow somehow. So we can think of flow itself. So we think of a flow. So what is flow here? Flow is the amount of water you push on an edge. So for every edge, there's some number. Okay, so you think of flow as a function from all the edges to the reals, the positive reals, right? And now we can express the constraints on flow as equations involving f. Right? So for example, what is the constraint that says that there is you can't violate the capacity of an edge? Well, imagine that I have the capacity of an edge is again a function, which is a function from E to R plus. And so the capacity constraint I can think of as f of E is less than 2. Right? That any flow you put on an edge must be less than or equal to the capacity of the edge. So now let's define some notation. Let's just say for any vertex V, n plus V is equal to the set of edges V comma W. Is it, sorry. Yeah, actually that's correct. Set of edges V comma W. V comma W. E. So set of edges going out from E, and n minus V is equal to the set of all U comma V. So I can actually write this more concisely just this way. Right, so this VW, that's U comma V. Right, so edges going in, edges going out. So for example, for this vertex, if I have all these edges going out and these edges coming in, right? This is n minus b, and this is n plus, right? Now once I have that, I can express the flow constraints, namely, for all v, the sum over the edges in n minus f of e should be equal to the sum over all edges in n plus v, f of e, if v is not equal to the source or the sink. So what you're saying is that for every vertex that's not the source and not the sink, the amount of flow coming in has to be equal to the amount of flow going out. And why do I have to put that caveat? Because I'm allowing the source to produce water. So there's always flow going out of the source, but nothing coming into it. There's always flow going into the sink, but nothing coming out of it. So for those two, this doesn't apply. For everything else, this must apply. Okay? And then the goal is to maximize the flow coming out of the source, which is going to be the sum over all E belonging to n plus s f of E. Okay. This is the total flow going out of the source, and this is what we want to maximize. Because whatever you push out the source is going to end up in the sink. So that's it. Is that clear? Okay. And what do I want to say? How do I express the observations involving cuts and flows in this language now that I have a formal notation for this? I can say that for all cuts S, right? And for all flow, let's call this a feasible flow. Feasible flow means it satisfies all the constraints. Feasible flow F, and not for all cuts, for all ST cuts, because that's what you want to say. Cuts separate the source from the sink, right? We can say that the flow value, the sum of E belonging to n plus s f of E, is less than equal to the sum over all edges in S, CL. This is what we just said, that what we claim to be true, that the sum of all, that the total flow must be less than the capacity on the thing. Right? Yeah? So now we have the right jargon and notation set up to think about this question. Right? We haven't proved this point here, so I'm going to put a question mark around this. But this expresses that thing we want to prove. And so just sort of as a side note, right? If you're trying to prove something and you're struggling to sort of say what you want to prove, it might mean that you need the right notation to sort of say it more precisely. Right? I want to get to a point where I can make a formal statement of what I want to show. This is an inequality, it's either true or not. I can actually now try to prove it. But I have to use a notation to get there. Okay? And again, sort of a harbinger of the fact that this is hiding a deeper, what is called linear programming structure, is the following observation. That I don't, okay, hold on. Sorry, never mind. So if you had to solve the flow problem using the techniques we've seen before, okay, not new techniques we've seen before, there's a very natural technique you might try. Namely, you might try a greedy strategy. Okay. So what would a greedy strategy look like? So let's go back to our graph that we drew here. I'm going to copy this out. what would a greedy strategy look like to solve the max flow problem on this graph? You maximize the flow from S to. Yeah?
Start at A,
Yeah?
and then just take the max.
Take the best edge you can push out.
Yeah, and then continue that.
Okay. So let's try it. Let's take the best edge you can push out and try pushing out some flow. So we have the edge of capacity 10. Now remember, we're not really required to only push on one edge, but let's start somewhere, right? So we can start that. So okay, 10 seems good. Let's try to push 10 units of flow here. So we push 10 units of flow this way. Right? Now we've got 10 units of flow coming into the next vertex, and we can't push 10 on any one of them, but we can push 7 on one and 6 on the other. So again, we'll put 7 on one and 3 on the other. Right? So you'll put 7 here, and you'll put 3 here. Okay, there's 3 coming down there. Now that 7, it has basically, I don't think I put in, let's put a number over there. Okay. So now that 7 has, I can't do anything there, so I'm kind of stuck, right? So that seemed like a bad idea. I pushed too much flow and I have to back up a little bit. Okay, so let's just say, fine. I'm willing to, realize that, okay, I should have only pushed 4 units of flow and not 7, which means it turns out that here I could actually push 4 and 6, and that would work too. Right? So there's not an algorithm here. This is still very easy way of doing here. So I push 4 here, 6 goes down there, then 1 and 3 go that way. Right? So now I have 1 going here, 1 going here, 3 going here, and the 6 come down here. Right? So now this one, it can't do anything, so it just goes in and just continues on to the end. That's good. I want you to flow to the end. So that's my little victory there. I've got 3 coming down here. Now this has got 6 coming down here, and there's 8 I can possibly send out. So I'll just send 5 here and 1 here. This 1 and 3 come down here. Well, that didn't work because it's too much. So it really should have only been 1 coming down. So that reduced even more. So that became, instead of 4, it became 2. Right? So 2 coming down there, and the 6 stays here. That becomes 8. So let's see. So I have 2 here. It goes till here, and that goes up there, and this 5 carries on here. So I've got, basically, if you summarize all this, I have 1 and 2 and 5. Total of 8 units. Is that right? Or did I do something wrong?
1, 2, and 2.
Sorry?
I have
Too much.
Yeah.
That's something wrong here, right? How did 5 go? There's no way for 5 to go, because I only used up 2. Which is another clue, right? If I look at the amount of capacity going into the sink, there's only 6 units of flow. There's no way I can get more than 6. That's because I doubled up here. So I have to adjust at some point, and I'll end up with 6 units of flow here. So this will actually be, this is not 5, this is going to be 3. No, not 3. This 2 is going to be, what's it going to be? 2. 2. It's going to be 2 here. Because there was 2 from there and 2 from here. So this is basically a total of 5 units of flow. Okay? Okay. You will observe now that this edge, I'm going to mark this with getting the color. This edge here, this edge is full. It's done. No more flows in time. My only hope is to get 1 more unit of flow coming in through here. But that edge, this one is full. So I'd have to get it from something from here somehow. Right? So in my greedy strategy now, I can try to push out more flow, but now I'm stuck because these are both full. So I might try to come here and do something, and I can't go anywhere because these are now stuck. So if you play with this a bit more, you will see that I can't do anything more. And maybe I could, I don't know. I have 6 units of flow there to dispose of, but I'm only at 5. And so there's no easy way to tell now whether my greedy strategy has done something useful or not. And if you play with this some more, maybe a modified example, you will find out that the greedy strategy will in fact not get you the optimal solution. And the reason is that the greedy strategy, like most greedy strategies, is making some local decision based on what to do. I even gave it some help by saying, okay, I'm going to backtrack a little bit, but really it's making some decisions about what to do, and it's committed to those decisions, right? And if you want to be able to change your mind, you have to build a backtrack in some systematic way. But backtracking is very expensive. You can't really enumerate over all possible ways of doing this. So there has to be a better way to think about backtracking. So on that note, I see we're out of time. We will talk about this on Friday. And I'll talk about how to design a backtracking procedure that's systematic and gets you this. So I should say today, I will be in my office till about 12:15, but I have to go for a faculty